So take my word for it. You are not going to do better than the experts if you try to develop any of the software, but you can benefit from their knowledge by reusing their package. And it's really easy to do it. So let me show you how it's going to work. So we're going to start with a package called bcrypt, which is not the most recent one, but it's cross-platform, and you can get results that work in a variety of different languages, much like MongoDB. So we're going to start by pip install bcrypt. And then I already have it. So Python import bcrypt. And then there are basically three methods or three functions in the bcrypt library that we're going to take advantage of. So the first thing is a method called gensalt. And we'll say salt is equal to bcrypt.gensalt. And then there's an optional parameter here called rounds, which is, you give it a number, which is a work factor. And basically, the bcrypt hash function is slow. And mostly when I talk about code being slow, that's a bad thing. But when you're talking about cryptology and cryptanalysis and breaking passwords, breaking hashes, slow is good, because slow means it's really, really expensive to brute force it. If it takes you a half a second to test out one password, and you need to test out 1 million passwords before you find the right one, that's 500,000 seconds in order to break the password, which is not a practical amount of time. That's a long time. So rounds is a trade-off between how many rounds of hashing it has to go through before getting the final value. Basically, it takes the hash function is going to take a password, and it's going to run one round of hashing and come up with a hash value. And then it's going to run a second round of hashing and hash the hash value into new hash value and hash that hash value into new hash value. And basically, the number of times it does that is going to be controlled by this rounds number. But it's not just linear. It's not like rounds 5 does 5 passes of hash, and then round 6 does 6 passes of hash, and so on. This is actually the power. It's going to raise 2 to this power, and that's going to be how many times it does the hash. So if I do 8 rounds here, that actually means it's going to do 256 passes of the hash function. And if I do 9, that's 512, and 10 is going to be 1,000 times around, all the way up to like 16. That's, 65,000 rounds of hashing just to generate one hash value from one password. Okay. Now on my systems, which are pretty zippy, I can get away with about rounds 12 before that starts making logging in awkward. So let's try salt with 12 rounds, which is, was it 2048? Something like that. And then the actual hash function is going to be hash equals bcrypt dot hash pw. And then I give it a password, like should be something reasonably secure. Like I like passphrases rather than things with a bunch of funny characters in it. So like this is reasonably secure just because the length makes brute force intractable. Period. And then this hash function, it takes binary strings. This is actually a text string. And the difference between a text string and a binary string is that text strings have encodings. So this is probably UTF-8. There's also an encoding called Latin 1, and then there's one like UTF-16, which is wide format Unicode, and so on. But bottom line is that the string has an encoding, and what we want to encrypt or hash is actually just a chunk of binary data. So it's easy in Python to convert a piece of text into a binary value, binary buffer. There's a encode method, like so. And this will turn this string into binary. And then the second parameter here is going to be a salt. And that's it. So you execute that. Here's the salt. And B at the beginning here means binary. So this is a binary string. And then my hash is that. And you'll notice that the hash value includes the salt as the first part, and then an actual pseudo-random number value after that. And this is all being encoded to display in ASCII, but it's really binary data. Okay, so a hash includes both the hash value and also the salt that was used to hash the password. Okay, now it includes the salt because when I go to check the password, it's going to use the same salt in order to compute the hash. So how do I check a password? I say bcrypt.checkpw, and I give it a password. This is not a reasonably secure password. It is though. And then I give it the hash. And that's false because it doesn't match. If I want it to match, this is a reasonably, I have to type it exactly. This is reasonably secure just because the length makes brute force intractable. And that matches. So if you give me a password in plain text, I can pull the salt out of this hash value, hash this password with the same salt as I used to create the hash, and then compare the two values. And if they match, I gave you the original password and I've proven that I'm me. And if they don't match, then I have not proven anything. And that's how it works. So you store the hash, which cannot be reversed to recover the original password, assuming that this is reasonably secure. If it's only 4 characters, I can do a brute force search and find it pretty quickly. But if it's reasonably long, it will take too long to do that. So I store the hash. User gives me the correct password. I check it. If it matches, they're logged in. If not, otherwise.